Newton's law of viscosity. I think you have already studied this law. This topic you will get in the first chapter of fluid mechanics. Newton's law of viscosity. You know that here what is given as the law is that shear stress is proportional to the velocity gradient, where shear stress is denoted by tau, velocity is denoted by here u, and distance by y. So velocity gradient is du dy, du by dy. This is the velocity gradient. Therefore, according to the law, tau is directly proportional to du dy. Therefore, tau can be written as a constant multiplied by du dy. That constant is denoted by mu, and the name is given to that constant is viscosity or dynamic viscosity or coefficient of dynamic viscosity. You can get the dimension of mu by putting the dimensions of shear stress, velocity, and the distance y. Okay. Shear stress means it is force per unit area, therefore it will be force per meter square, and force is in terms of Newton, and that Newton can be written in terms of mass, that is kg meter per second square. So that way you can easily get the dimension of mu. Now the problem is that many students make one mistake. I have observed this, that they think that the direction of u and the direction of y are same. No. Here, direction of u and direction of y are not same. They are not parallel to each other. They are actually perpendicular to each other. For the explanation of this law, two-dimensional velocity field is assumed. You know, two-dimensional velocity field. Actually, all the fluid flow fields are three-dimensional. Changes of the flow parameters occur in all the directions, in all the three directions. But say, for example, in a given problem, in any one direction, say directions are given by x, y, and z. Say in the direction of z, the changes of the flow parameters are very small. Almost there is no changes. So that changes can be neglected at ease. So if such be the flow domain, where in one dimension, out of three dimensions, in one dimension, all the flow parameters almost do not change with spatial coordinate in that direction. Okay. So the velocity field or the flow domain becomes two-dimensional. So this will be called two-dimensional flow field. So let us consider the two-dimensional flow field is denoted by x and y. X is the horizontal axis, y is the vertical axis. Okay? X is the horizontal axis and y is the vertical axis. And the velocity is given by capital V. And you know that velocity is a vector quantity. So this vector can be resolved into two components, one along x, another along y. Let us assume that along x, the component of velocity is given by small u, and along y, the component of velocity is given by small v. Therefore, this capital V, that is the resultant velocity, can be written as ui, small I, plus v into small j, or I cap, ui cap plus v j cap. Here I cap and j cap are the unit vectors along x and y directions. So small u and small v are the velocity components along x and y directions. So here u can be written as a function of x and y. Again, v can also be written as a function of x and y. Now, these are the axes, horizontal and the vertical one. And draw one arbitrary velocity profile. Arbitrary velocity profile. And at a location y. Location y means it is a perpendicular distance from the x-axis in the vertically upward direction, in the direction of y. Okay. So at a distance y, you denote one point on the velocity profile. Suppose at that point, the velocity is given by u, where the location is denoted by xy, x comma y. Means coordinate of that point is given by xy. And after a small interval of space delta y, which is infinitesimally small quantity, you take another point on the same velocity profile. So here the vertical distance becomes what? It becomes y plus delta y. Okay. So this becomes the y coordinate, y plus delta y. And let us assume that the corresponding x coordinate becomes x plus delta x. And at that location, at that point, the velocity is given by u plus delta u. Delta u is the increment in velocity. Maybe delta u positive, again it may be negative also. If velocity increases, delta u will be positive, and if velocity decreases, then delta u will be negative. So at the location x plus delta x, comma y plus delta y, the velocity in the direction of x means u component of velocity is given by u plus delta u. So between these 2 points, here u plus delta u. What is the difference in the velocity? It is u plus delta u minus u. U plus delta u minus u. So what is the result? Result is delta u. That is the velocity difference between those 2 points. Between those 2 vertical points, okay? That is the velocity difference. And what is the difference in the vertical distance between them? That is y plus delta y minus y, that is delta y. So what is the velocity gradient at point xy? The velocity gradient will be there, that delta u difference in the velocity divided by the difference in the distance. Delta u by delta y. And in the limit, means when delta y approaches 0, delta y tends to 0. In that case, that del u del y will become du dy. Okay, that delta u delta y, delta u by delta y will become du dy. So this is the velocity gradient. So according to Newton's second law of motion, shear stress at point y. So what is the meaning of shear stress at point y? Shear stress is equal to what? Tangential force at a given surface divided by the area of the. So we are talking about shear stress at the location xy. So how you will calculate shear stress at the location xy? At the location xy, there is one point. The coordinate of that point is xy. Now, surround that point by a small, very small, infinitesimally small area. That area is parallel to xz plane means horizontal plane. That area is parallel to xz. X and z are the horizontal axis. Y is the vertical axis. Okay. So surround that point xy by a infinitesimally small area. That area must be parallel to the xz plane. And consider a tangential force on that small area. Tangential force. Force may be in any direction. Now resolve that force into two components, one along that tangential surface, means along xz plane, and another one along perpendicular to that, that is along the y direction. Okay. Okay. So you now consider the tangential component of the force. So tangential component of the force divided by that small area, which is infinitesimally small, will give the shear stress at a point xy. Right? Will give shear stress at the point xy when the area is infinitesimally small. The area approaches 0. Area tends to 0. So that is shear stress. So shear stress at the location xy is proportional to the velocity gradient du dy. And this is Newton's law of viscosity. And therefore that shear stress is equal to a constant into velocity gradient. That constant is denoted by mu, and this is called viscosity or dynamic viscosity or coefficient of dynamic viscosity. If temperature is held constant during the course of the flow, then viscosity remains constant. It does not change. If temperature changes, viscosity may change. So effect of temperature on viscosity will be discussed in the next lecture. Okay. Today's topic was just about Newton's law of viscosity, and this is Newton's law of viscosity. Follow any book, you will get idea about this law. Okay. Okay, thank you.